Okay, so as Aidan said, today I'm going to be talking about earthquakes and landslides and rain, so the aftermath of the 2008 Wenchuan earthquake. So this is my PhD, and I've been spending the last 4 years on this, so hopefully I can explain it to everyone eloquently. So I've separated my presentation into four parts. So the first part is just a brief overview of kind of what an earthquake is and how they produce landslides. And the second part is to look at kind of the impact that landslides have on communities that are affected by earthquakes. And then finally, just to look at the impact of the immediate impact of the 2008 Wenchuan earthquake, and then its aftermath. So what is an earthquake? You know, I'm sure most of us have seen, whenever there's a large earthquake that's big enough to pique the interest of the media, you see all the news sites are flooded with images of cracks in roads or destroyed buildings, or potentially even areas with massive landslides that have been greatly affected. But they don't often discuss kind of what exactly an earthquake is and why they're so devastating. So I thought I'd cover it briefly to make sure we're all kind of in a similar idea. So earthquakes are generally formed by the interaction between different parts of the crust, either moving towards each other and colliding, or moving side to side away from each other. So the Earth is made up of lots of large blocks called tectonic plates, and when they move together or apart, there can be a lot of friction between them. So as we can see here in this little diagram, we've got two plates sliding up against each other. So one's going up, one's going down, but where they connect, there's a lot of friction. And so in small areas, the plates can get stuck. And as they get stuck, they begin to store energy, and they'll keep storing energy until the strength of the rock is overloaded, and in which case you see this massive snap happen. And when that snap happens, all of the energy that's stored up by the earthquake shock waves out into the local area. So when that happens, generally there are 4 different types of waves produced. So we have these P waves and S waves, which go deep into the ground. So they don't produce very much shaking at the surface. But these other two, the Rayleigh wave and the Love wave, these primarily affect the surface. So the Rayleigh waves pushes everything up and down, and then the Love wave pushes everything left to right. So you can kind of imagine that in general, unless they've been designed for it, most buildings don't like being shaken up or down or left and right. And then in mountain ranges, the same thing happens. You know, anything that's loose up on top of a mountain range or quite close gets all shaken up and can begin to collapse. So that's what we saw in the Wenchuan area. So these are 2 different images that are quite close to the epicenter of the earthquake. So this first one is nice and green. There are a couple of landslides here and here, because landslides also occur when it rains. But when the earthquake happens, you know, we see all of this green turns into a big mishmash of white and green. So all of these white areas are recently formed landslides. So the tops of the ridges are shaken so much that big cracks in the rock form. All of the trees and everything that's holding the soil together just gets ripped and teared and broken, and then it all just falls down the mountainside. So it can land in the rivers, or quite often it can just fall and land halfway down the mountain range. And then because these areas are so steep, when people live there, there's not a huge amount of area for them to live. So they're in these incredibly densely populated areas, on like the only real major flat areas in the landscape. And unfortunately, because all the flat areas are bottom of these steep slopes, when an earthquake happens, not only are they devastated by the shaking, they're also devastated by landslides that form and destroy buildings and roads and stuff like that. So they have to deal with kind of two threats at once, which can greatly affect how long it takes for these areas to recover. So I thought I'd briefly just run through where the Wenchuan earthquake happened. So the Wenchuan earthquake happened on the 12th of May 2008. It was I think it was like a weekday, Thursday potentially, and around 2 o'clock in the afternoon. So it occurred near, the epicenter was near this town called Yingshu, which is just here in the Chinese province of Sichuan in the southwest of the country, and it's fairly close in global terms to India. So as we know, the Indian subcontinent plate is moving in this direction in towards China, which forms the Himalaya, and then the Tibetan Plateau, which are some of the highest areas in the world. And all of this energy that's kind of stored up by the tectonic movements moves it towards, in a southwesterly direction, in towards China and Myanmar, which creates some of the largest earthquakes that occur on the planet. So I just got a little video which we can just see, so it allows us to see where the epicenter is and kind of what it looks like at the present day. So we just flew past on the video Chengdu and Chongqing, which are two of the largest cities in China, and then effectively the world. And so both of them felt shaking from this earthquake. But then, so the epicenter of the earthquake is just in this area here. And then we have the town of Wenchuan, and then all of this is the county of Wenchuan, hence the name. And then we can see in these mountains, there's lots of white patches, and nearly all of these white patches are landslides which were caused during the earthquake. So we can see that the shaking here was huge. It was a magnitude 7.8, which is one of the biggest earthquakes that China's ever seen, and one of the biggest that you can get on planet Earth. And it caused a huge amount of devastation through the shaking and through the landslides as well. So we can see like a small snapshot of that here in Beichuan town again. So Beichuan is the opposite end of the fault to Wenchuan that we just saw. So initially people, the government wasn't aware of quite how badly Beichuan was damaged by the earthquake because it was so far from the epicenter. But when they finally got there, they found that not only had it been completely destroyed by the earthquake, but these large landslides have caused even more devastation. So this large one here caused 1,600 casualties, and then this one on the other side of town was, while being a smaller landslide, it collided with the local middle school, and as it was during the school day, unfortunately, most of the children there in the school died. And then the other thing to notice here in this picture is that we have this major river running through the center. And despite it being a massive river, there isn't actually a lot of water in it right now when this picture is taken. This picture is taken just after the earthquake. And the reason why there's not a lot of water currently is because just upstream of it, there was an even larger landslide. And that landslide blocked all water, creating a temporary dam. And then a couple of months after the earthquake, during the summer rainy season, that dam failed and caused a massive flood to come rushing through the town, so adding yet another layer of devastation onto the area. You know, this area was so devastated that the Chinese government decided it was easier to actually make a new town for everyone in a much safer location, and this area is now kind of preserved as a memorial to the earthquake itself. So just to run through some numbers, the Wenchuan earthquake caused over 87,000 deaths and over 60,000 landslides. And if you combine all of these landslides together, they produced over 3 cubic kilometers of rock and soil. So that's huge amounts of rock and soil stored in loose sediment piles all over the mountain range. Some of them are in rivers, some of them are high up on the mountain range, and most of them are completely unstable. So the next time it rains, and it rains a lot in China during the summer seasons, that they can get completely washed out again. So, which we can see in this kind of video. So when it rains, all of the sediment, all of the rocks and the soil mix with the water that's pouring into the mountain streams, and across the mountains, and interacts with the water, interacts with the soil, and turns into these massive flows of mud and rocks and boulders. And then it all just rushes downstream at quite a big speed, and it can completely crush buildings and destroy newly rebuilt roads and bridges, and block rivers and all sorts of stuff. So it just adds on another layer of devastation, another layer of risk and stuff, potentially years after the original earthquake. We can see in this video here the size of some of these boulders being pushed along by the flow is just huge. So the idea of my PhD initially was to identify, or try and identify, just major factors in why these things occur, and potentially look at identifying areas that are at risk in the future. So the first thing we did was create a database of all of the large debris flows that had occurred since the earthquake. So here we've got the years along the bottom and the numbers of earthquakes that occurred in that year, debris flows that occurred in that year. So we estimated at least 150 debris flows occurred in the 8 years since the earthquake, and a lot of them occurred in the first 3 or so years after the earthquake. And we can kind of see that there's a rough trend of the number of debris flows decreasing through time. So it's important for us to try and work out as well, not only where these debris flows are coming, but whether they are becoming less frequent through time. Because if it's a very short-lived effect, it may be something that becomes more manageable through time, and something that's not necessarily needs a significant investment. Or this could be some kind of false trend, and ultimately, in 3 years' time, we could get another 80 or so debris flows. So the way that we wanted to go about it quite simply was to look at the 3 things that debris flows need to form. So the first thing is they need suitable sediment. So they need sediment that is that can easily absorb the water and interact with the water, that begin to start to move. You can't just have huge amount of boulders, and you can't just have lots of sand. You need to have a good mixture. The second thing you need is topography. So in this case, you need steep sides. So you need either steep mountains or steep mountain rivers to get things moving. If everything's too flat, things find it difficult to move, or if the stuff does start to move, it moves slowly and it won't actually be danger to anyone. And then the final thing we need to know is, like, how easy is it for water to get into the soil? If it's high up, there's not a lot of water available, whether if it's in a big river, lots of water can move through it and potentially cause more landslides, more debris flows. So the first thing that we wanted to look at is kind of the changes in the landslide deposits through time. So we can do that through satellite imagery. So we can see here all of these big white patches are landslides that were caused by the earthquake. So this image was taken in 2011. So anything that's white means it's fresh and it's loose and it's easily movable the next time it rains, potentially. And anything that's thin like this is a debris flow itself. So in 2014, we can see that everything's kind of changed from that bright white to these greys, and then potentially even been revegetated by these green and red plants. So this could suggest that this sediment has become more stable through time and is no longer able to be mobilized. The other thing that we can see here in the left is that the river has been filled up with sediment from further upstream. So this could be potentially due to a debris flow running through it, or smaller debris flows have entered into the other bits. So this is also an area of potential risk in the future. And then if we go to 2018, we can see that while most of the area has begun to revegetate again, actually some areas have turned more white, brighter again. So this kind of suggests that maybe some areas look stable in one image, but actually in the next image they could potentially fail again if a new rainstorm comes in. So that's something, again, we need to look at and be aware of. So the next thing we wanted to look at is whether the size of the landslide deposit matters. So what we did was we separated all of our landslides that we mapped into small ones, so these are in red, or large ones which are in blue, and then we looked at where they were in relative to each other in the landscape. So on our y-axis here, we have the slope. So this tells us how steep the area is that the mountain ranges, the landslide deposit is. So if you're up here, you're in a very, very steep area, probably right at the very top of a mountain range. And if you're down here, you're completely flat. So you're probably at the bottom of a valley. And then along here on the right, on the x-axis, we have the drainage area, which is basically a measure of how far you are from the ridge. So if you're here, you're right at the very top of the mountain, and if you're down here, you're likely to be in quite a big river. So what we can see here initially is that the smallest landslide deposits are quite a way up the mountain. So they are, on average, they are quite near the top of the mountains, which is kind of what you expect because they're small. Whereas the larger landslide deposits are quite close to the rivers. So this kind of suggests to me that if one of these is more likely to fail than the other one, you can initially have potentially an effect of water availability. So if the larger landslide deposits fail more easily, it could be because they have more water. Whereas if the small ones fail more easily, then potentially it's because of the steepness of the mountain range. So what we see here in this second graph is how much the total volume of debris flows that exited the different types of different sizes of landslide deposits. So in red here we've got the smallest ones, and in blue here we've got the largest ones. And what we can see is that the smallest landslide deposits produced almost 2 times the amount of land deposit, almost two times the volume of debris flows than the largest ones. So this is potentially promising. You know, it tells us that the smallest landslides could be more deadly than the largest ones after the earthquake. But you have to remember that in this red, there are over 7,000 landslide deposits, where in this blue there are just 62. So immediately you can see an issue here of trying to identify which of these 7,000 landslides is likely to fail next is quite a big ask. So we need to take another step basically. So the next thing we can do is look at how the location of debris flows may change through time and where they trigger. So again, we've got slope on this y-axis and then drainage area on this x. So if you're up here, you're right up on the ridges of the mountain range. And if you're down here, you're in one of the biggest rivers in the mountain range. So what we can see immediately is that straight after the earthquake, most of the debris flows occur on the hill slopes, not in the rivers, and they occur on quite steep slopes. So they don't need much water to fail. It rains and they're happy to go turn into a debris flow. But as we come to the end of our observation period, so we were looking for the 10 years after the earthquake, we can kind of see that slope becomes less important because we've moved down slope and we've also moved to the right. So this dotted line shows us where the rivers start. So now all of the debris flows are sitting within the river channels. So this suggests that while all of the landslide deposits that are on the hill slope were important at the start, at the end of our observation period, it's actually the sediment that's in the rivers that's important. And we have to remember that this is taking place over 10 years, which is really quick when you think about things in terms of geology and stuff like that. So what that really means is, like, if we put a prediction of how many debris flows and where they would occur in 2011, by 2018 those predictions would be completely wrong, and we'd be completely underestimating the risk of all of the debris flows happening at the bottom of the channels rather than those that are happening at the top of the mountainside. So at the end of my PhD, could I predict any better where debris flows would occur? And, you know, as always in science, there's no potential yes or no. It's a nice maybe. So initially they occur in small landslides on steep mountainsides, but there are thousands of these, and the deposits, the conditions within the deposits change so quickly that we can't really make any predictions that can last a long time. But we do notice that towards the end of those 10 years, everything begins to move down slope and everything in the rivers becomes much more important. So potentially we could begin to focus on those instead. And then one last thing, while we weren't able to work out kind of where the debris flows were happening, we were able to estimate how much sediment was being moved by those and other processes. So if we look here on the left, we were able to estimate using, we drew around our landslide deposits, we drew around our debris flows, and we were able to estimate volumes associated with those. So our hill slope deposits, by the end of our observation period, stored around 88% of the total material produced by the earthquake. So the majority of material is still up there in the mountain range, still in hazardous locations. And then if you look down here at the bottom into the Mingyang, which is the major river in this mountain range, only around less than 13% of the material has entered into this river. So if it's entered into this river, it can no longer fall on anyone, it can no longer produce a debris flow or anything that could potentially be hazardous. So the fact that such a small amount is no longer hazardous suggests that the effects of this earthquake could potentially last for a very long time, and that debris flows could be an important process in landscape evolution over hundreds or if not thousands of years in these mountain ranges. And yep, that's it. Thank you.
Great, thanks, Ollie. That was really interesting. Um, a reminder that if anyone has any questions, you can drop a question into the Q&A box, and you can do so anonymously. So there's no such thing as a stupid question. But if you manage to find one, we won't know it was you. In the meantime, while we wait if any questions come in, I had a question for you, Ollie.
Yep.
How unique is this kind of the evolution that you see over the 10 years from this earthquake? How unique is that to this region? So like, do these same kind of rules apply to other regions with the kind of landslides moving downslope? Like other regions in the world, how applicable are these observations to?
So they should be pretty applicable to any mountain range that's steep enough to have frequent landslides and major earthquakes. So we know there was a large earthquake in Taiwan in 1999 where we saw very similar effects. So most of the material gets washed out a small amount of material gets washed out very quickly, and everything kind of stays still. And we see something similar in Nepal. So there's a big earthquake there in 2015, where we see lots of debris flows in the first couple of years after the earthquake. Then everything kind of stops, but all of that material is still there, and it's still not known particularly if that material is going to collapse immediately or will happily stay there for hundreds of years.
Cool, thanks. A couple of questions have come in. The first one, thanks for your interesting talk. I wonder, how do you quantify or measure the portion of sediment remained at the hill slope and the channel? Thanks.
Okay. So you can estimate the volume of landslide deposits from their area. So you go onto Google Earth, you draw a polygon around the area, and then you can use area to volume scaling ratios. So they basically assume an average depth effectively. So you convert them all into a volume. So that gives you your total volume. And then the next thing we did was through time, we mapped these landslides again and again and again. And we mapped whenever we saw activity within those landslides. So we saw a landslide within a landslide, we would map that second landslide, and then we could use that area to take away how much volume had been removed from it. And then we could do a similar thing if there was a debris flow. We used a slightly different scaling relationship because debris flows are complicated, but that's effectively what we did. And then with the tributary channels, we assumed a triangular cross-sectional area, and we kind of just measured different cross-sections through time and just measured the changes, whether they were expanding, so the area was increasing, or whether they were shrinking and being incised. I have a paper that's potentially in review, so hopefully that will come out soon and clarify any more questions of that.
Great. So actually on the topic of the satellite images, we have a question asking what sort of frequency and resolution the satellite images used are, and what would be more optimal, knowing all you know now? Is it higher resolution, higher frequency in those satellite images?
So the resolution of them, I think at best was like 1 meter, and at worst was like 5 meters. So they're all pretty good. When we were mapping things, we had some aerial imagery right from the start, and then as we got towards the end, they were mostly satellite images. We mapped everything whenever we possibly could when it was cloud free. So we've got an image from 2008, and then 2011, 2013, 2015, and then 2018. So we have a reasonable coverage of those years. So obviously everyone just wants more frequency and more resolution. whenever they possibly can. But I imagine higher resolution would be useful to measure more accurately the exact processes that are occurring, whereas frequency would be more useful to kind of understand, you could map potentially closer with rainfall data. So you could map rainfall thresholds and things like that much better if you had the data, more data available.
Great. We have another question, which is, did you map the underlying geology, and did the rock type or structure influence the landslides?
I didn't look too much at what caused the landslides themselves, but many other people have. And what they found is that most of the landslides occurred in quite loose, highly weathered sedimentary rocks. So this area has some big granites in it, and then it has lots of seabed sediments, so lots of shales and quartzites and sandstones. So all of those weaker rocks produce a lot more landslides than the harder granite rocks. But potentially there's a difference in the landslide types that they produced. So there's quite a lot of interesting things there.
Sure. Loads of questions coming in. Maybe we'll pick up one or two more. There's one here. Do automated methods now exist for mapping landslide area that would allow you to do this analysis in other parts of the world?
So yeah, people do use automated methods for mapping landslides. They're not completely automated, unfortunately, just because the remote sensing by algorithm is very difficult, because you get lots of false positives. So even if you're just trying to identify change, it can identify things wrongly, so you have to go through and remap those. But then the other thing they can also do is combine two deposits together, so you end up with a really big area. And so when you're looking at volume, which is more useful generally than the total landslide area, you can suddenly exponentially increase the amount of volume that you have, which can be a problem. So there's lots of pre-processing and post-processing. So while it's possible, it's perfectly valid to do manual if you're willing to sit there and get people to draw it. Luckily, we had lots of master's students in China who were happy to map it for me. I didn't have to spend the 4 years doing that.
And I suppose with pre-processing and validating, you can end up taking as long trying to automate it, I suppose. People
end up spending similar time, so it's debatable whether it's worth it or not.
Great. I think we probably have time. We can fit one more question in, if that's okay. Yep. We have a question: was rainfall measured over the time of study? Was it fairly constant? And does the overall amount of water available, presumably that's a key factor in the sediment flow, so were there particularly wet years with lots of rainfall, and how does that factor into?
So unfortunately, rainfall data is a little bit patchy over this area, and China is very difficult to get data out of. So while we might know of some areas where there is really good recording of rainfall, we weren't able to access it. So instead we used satellite imagery. So you can use techniques that NASA use to estimate how much rainfall potentially falls based on, I'm not entirely sure, but based on how much water is in the air, I guess. And you can convert that roughly into precipitation. Using that, we found that there isn't a huge amount of difference through the years of how much rainfall there happened. So the biggest year for debris flows was 2011, but there was rainstorms of similar size in 2016, 2017, and they produced a lot less debris flows. So the main reason why we're seeing less debris flows is probably because there's something happening to the landslide deposits themselves rather than any external factors.
Great, thanks. I think we'll wrap up there. Thanks for a super interesting talk. It has been recorded, so hopefully if anyone would like to watch it back, it will be uploaded to, I believe, the department Facebook. And equally, come along same time next week for another talk, and then every Wednesday after that until the 18th of November. Thanks, Ollie.
Yeah, thank you. Thanks, everyone.